Hello again. Let's move on to the next speech, the next presentation. I will be flexible with Abel for you to settle. Absolutely. Abel should speak and talk is very intense. By the way, be ready. Be ready. Abel does not need too much introduction. Abel is a super good guy. We have been enjoying fabulous speeches from him, his collaborations and roundtables. Valero, introduce yourself. Oh, thank you. Thank you for coming here, my friends. My name is Abel Barrero. I'm known on the internet as a Squatter. On Twitter, I'm on Sangin Hour. I'm a CTF player with Amnesia team. I collaborate with R2 project for the past 1.5 years, and I've been a malware analyst for Panda Labs security for some time. So, as Roman said before, this is gonna be a very technical speech and thought. I will talk about assembly language. I would talk about rootkit and bootkit. You can see a bootkit definitions is code introduced into the system, which gives us the maximum privilege possible. By the way, rootkit or bootkit are not bad per se. Their intention is to facilitate, to enable us to do something by analyzing the virus by the name of Romney's example. When you start up the computer on BIOS, when you boot it on BIOS, we can apply it, but this applies specifically to BIOS. Before starting, let's clarify the nomenclature. The master boot record. When you boot the computer, BIOS look for the devices on the system and gives the control to the master boot record. Then the B VBR volume boot record takes over from MBR on the operating system. So let's talk about the system is booted. When you plug in the computer BIOS stars, it gives number to the launching devices. It's going to read 5012 BIOS and looking for signature 55. And the computer says this is a launching sector. It's going to be stuck on memory, and this is the MBR. When it's mapped on memory, VBR takes over from it, which is not launch or state which is located on the partition system. In some place, we need to know what partitions are located and the rest many information for the executed code charged by and loaded by BIOS. Located on the right thing. The master boot record contains initial part, which is code, then the, the partition tables, and finally the signature O per 55 O per AA. This takes up to 512 bytes, and the remaining information in their respective partitions. Each partition table created under the system disposed and has this identificating value on Windows. For instance, in the case of a swap, there would be a different number. 80 number is activated for Windows partition. Then the initial CHS value, how much is the space takes on the system, the initial sector. So let's move on to this field. We read it. After saying this is the active one, we go to the field 0 active partition. We start here. We can read the number here, and let's move on to the sector, and we'll be on Google VBR, very similar to the previous one. Volume boot record. It has a jump onto code, and there is some archive system heading. In here is information regarding the Windows partition. If it's NTC partition, it houses information regarding to the partition sector. FAT, and so on. I'm speaking very quickly. The volume boot record, the code VBR will be initializing the whole system. This VBR can differ among different systems. For Windows XP is NTLDR, for Vista is Boot Manager, and within open source multi-system is GRUB. On Windows, you have the partition part to be launched, so you can choose on the system how to launch the system. How to initiate to start up Windows Vista 7, 8 through 10, which are the most current systems, from BIOS to MBR 13, and loading the BVR, and then boot manager takes over from the previous one in real mode. We cannot direction it and address in memory one single mega. Here is one available 1 mega in memory, no more memory available. Here this kind of turns the BootKits. BootKits need to get by this remaining space in 1 mega. Once the boot manager is active, so the code is in 32 bits with established security precautions levels. This is the initial launching. Window jumps and uploads as necessary. If something is hibernated, Windows Resume will perform the necessary functions for Windows to use the anti-kernel. I'm speaking very quickly, and you can execute man tests, except as you can see on screen, this is how a system launch and boots since we press the button on the computer. Now bootkit analysis. All this information, the moment I will start analysis, I have no idea. I get hard disks and I start to analyze, and I noticed that the analysis with this roughnecks, as I check on the internet, it's the very first type of roughneck using the VBR partition system launching, compatible with XP Vista 7, 8. In 8 is not on 8 is not working properly. It's not because of the booklet per se. Um, they cannot elevate privilege to install these archives. If you do it manually, it works properly. It works even in on Windows 10. Is obfuscated polymorphic code distributed as a kit. The server of this bootkit was created at the moment, and there was a key behind, and it was seen as a bootkit. You can set up your own space. It's like a carrier for people to put their malware. Bootkit guarantees that you're gonna have a virtual archive system when somebody is looking for something onto the system to notice them, but Git will falsify and will tell, I'm not here. I have options to load from the kernel itself. The bootkit objective is to register a driver by ignoring all Windows measures. Here they don't play with the deactivation of the security plays and the signs they are in developer mode. Here it uploads the driver as a legitimate one. When I start the static analysis with IDA, I open the IDA file. We can see some comments. It's obfuscated code with grouper function, which obtains the real function they took for making the obfuscation, because they want to complicate our live analysis and to allow to conduct the polyformism phase of the builder of the virus. These blocks of codes maybe here or upstairs, downstairs, to guarantee that they create a table, they put it on some place, and it's working from here. And the function is this function will check on the table where they have to go to the place 17 on this table. This function is called obtain offset. When you open this, it's absolutely real mess. There's the assembler, and you need to analyze. The original code for RobNet is obfuscated, and it loads a cipher driver with profile cipher as well. When you boot this, it's a cipher code. It hides so many things for you not to see. So I create some execute scripts to calculate addresses and so on and so on. You get the key and you obtain the code. Once I have applied the ex, execute scripts, I get a very legible key with all the functions totally identified. This is a dead analysis of a dead code. We can see the instructions, and I obtain all you can see on screen. There is a function I can identify at the very first moment. I have the rest of all, so I know how things work. After checking all this code, I draw the conclusion that this code is altering the vector 15 of the IBT, managing the interruptions in the system. When we are on real mode, when we are initialization the system, there are certain interruptions used by the system to verify the bootup. This code is established by a handler on protected mode, is that the hoop are on the IBT, the interruption description table. The, the IDT would be the IBT protected mode. So they are not working in real mode. They're called the IDT, and they're called, like you can see on the screen. So different binary patterns to establish patches on the system code. We localize a function which is loading cipher data directly onto the hard disks in their sectors. We can observe the proper mechanism of the depuration used to locate patterns. For example, for the extracted boolean, the buyer is installed onto the system. The code, as we said, takes control from the BVR, and to continue the analysis, we will need to depurate and purify the whole code to know where the hooks and patches are located. The most difficult part for all of these, and what I want to be focused, is to show you how to create a working environment to monitor and trace a real machine. We're talking about tracing our own computer processors, 64, the Pentium you have. No matter how much processor you have, it starts and boots on mode 86. For you to do all these things, we will need to depurate the real mode.
This we will do using Box. It will allow us to debug the BIOS, the master boot record, VBR, and the boot manager on the 16-bit side. Then we will need to debug in the protected mode. Here things get a little more complex. Windows in the starting files includes an auto-debugging protocol of their own. So we can get into the different parts of the starting mechanism. So it's boot manager coming in, boot manager 32. It's got a debugger, an internal debugger. When the system starts, you need a debugger in the system so you can trace startup. When that is handed over to winload.exe, that file is disconnected, is no longer in the memory. And when winload hands over to kernel, it activates the internal debugger for the kernel. That gives you a system where you can trace the starting procedure. As soon as we get there, and we can use WinDBG, we can use symbolic debugging. I have lots of addresses and offsets here, but you see the names of the functions, so you have an idea of what they do. It's quite descriptive. So let us take a look at the tools that we will use to carry out this process. We will need an emulator, which will allow us to emulate a real processor. And for that you got IE32. Here you have the URL, and then something to disassemble. The code, we'll use IDA, and we use a virtualized system. This is an emulator, this is a virtualizer. Emulators emulate using code, but virtualizers use the CPU itself. Intel gives you the ability to do virtualization using their systems. So what we're interested in is in a system where we have box with a VMware image and a system that has started already. We will have to access system files and read the boot manager, for example, which comes compressed. We have the 16 and the 32 bits executables, depending on the version of Windows. You see BMZip that will allow us to unzip the contents of that file. We will use a hexadecimal editor that will allow us to use to access the disk, HXD in this case, and finally a debugger, which will allow us to do the tracing, to investigate what we need, WinDBG. Or we can forget about half of this and use Radare 2, which gives us almost everything. Last weekend, on Friday, I was putting together my presentation, and I made a plugin for Radare 2, which allows us to do basically everything we did in the previous stage, in the previous slide. Anyway, I put this together on Friday, so I don't have too many images on that. Let's take a look at the configuration of the debugging environment. Not complicated, but there isn't too much information about this in the internet. There's video clips available, published by antivirus companies, but they never tell you how to configure things. The first thing to do is to create a virtual machine using VMware or VirtualBox, whatever you like best. But we need to ensure that we start from BIOS. VMware, when it detects Windows 7, Windows 8 or Windows 10, shows a screen like this. How do you want to start? Firmware through BIOS or through EFI? And then we need to ensure that the hard disk that we have within the virtual machine is as similar to a real hard disk as possible. If you say it's a 60 gigabyte hard disk and the file is only 10, the system will detect this. But we don't want compression. If we edit the disk with a hexadecimal editor, we want it to be as realistic as possible. And these would be the options that we would have as part of VMware. So to allocate as much space as possible and to store everything in just one file instead of distributing the information in different locations. So here we have the initial stage completed. Then we use a COM port and we set it up as a pipe server. That COM port will be redirected accordingly. So we configure the name of the pipe server and that's it. Not much else. We install the operating system, and once we operate that on the operating system, we need to tell Windows that we are about to debug the kernel, Win Manager, or whatever. The first thing to do is to tell Windows how we will be using those options. So we configure the debugging in a serial mode at that speed, baud rate 115200. This is what we do. The options are here. This goes for all debuggers from now on. They will always use that communication protocol, okay? Now we can set up the different internal debuggers. If we want to activate the debugger in one load, remember, the BIOS is loaded, VMR, Boot Manager 16, Boot Manager 32. Boot Manager 32 goes into WinLoad. So everything that happened before debugging at this stage. Before activating this, we do BC edit and we ask the system to copy. There will be a number of options in the menu. So the copy will be made using that name. I tell it to activate the debugging. Right, here we are. So we tell the system to activate the debugger. Debug boot on the profile we just activated. As soon as we start Windows, we'll see a startup menu and we'll be able to choose the option. If we choose this option, the internal debugger from Windows will be there listening for people to connect. We can do the same to debug the kernel for Windows. This is what is loaded after WinLoad. And the same again. We say debug kernel. That would be debugging only, not debugging boot, okay? We may be interested in having all these debuggers active. We may have a profile where we have both debuggers active. One is activated after the other. We input the name of the profile we're interested in, and the rest is the same. So we talked about WinLoad, we talked about the kernel. But what happens with Boot Manager that gets loaded before WinLoad? Do we have the opportunity to debug that? Well, Microsoft allows us to do debugging for the 32-bit version. Whatever comes before that, there's no options. When we activate this, we will need, come what may, to use WinDBG. Why? Because Boot Manager 32 is the one showing the menus. If you go into Boot Manager in debugging mode, there will be no loading of the program showing you the menu of options. So when you debug Boot Manager 32, it will wait. When you connect with WinDBG, you keep moving. In this way, with Microsoft tools, we can do traces of all those steps, including the kernel. But there's things before that, of course. And for that, we need box. Omnis uses user characteristics. It itself debugs the system to find code patterns. This it does by looking for x86 log entries from DR1 to DR9, and box in order to optimize. Box doesn't compile. If you want to activate it, you will need to recompile box. In order to recompile box, this is what we do. Not very complicated. We'll use a Linux box to do all the make files. It's just these lines of code. We do the tar, the cd, we edit this file, and whenever we see these lines, we add enable debugger and enable x86 debugger. What do these lines do? The first one activates the debugger for box. Okay? When it's started, box will show us an interface we can use commands with. And the second line activates the debugging for the processor so that we can have interrupts and so on. That's because we need to recompile box. If we don't recompile box and we run a machine infected, nothing will happen. There will be no infection. We then move on. Once we have recompiled box, we create the debug BXRC file. Just like copying and pasting whatever you have on the screen. And pay attention to this. This is the path to the virtual hard disk for the virtual machine. With this, we are ready to move into an environment to debug a real system, a processor. Okay, this is what we are debugging. So debugging a BootKit. We start by loading the file in IDA. The BXRC file, we drag it and drop it into IDA. So we establish a breakpoint at that address, 0000, semicolon 7C00. That is where the VBR is loaded. So we run instructions until we reach the VBR. Here I have a small demo. So that once you set the system up, you can start it. This is the box screen and the initial instructions. Here we have that hexadecimal address we saw before. It starts, it stops, it loads the VBR. Now the VBR will go into the code for the loader. This is part of the virus already in the bootloader. What we will see when analyzing is not a real ROSNIS. This is something I've modified myself. I've modified it so that you can understand the code, otherwise there's too much mess. From here, we'll see a lot of assembler. And before we take a look at that assembler, let's take a look at the memory map. Our processors may be really powerful, we may have as much RAM as we like, but when the computer starts, it's low memory we're talking about, 1 megabyte. This is the first megabyte. From position 0 in the address space up to position 1024, we have the IVT, the interrupt vector table, in real mode. It's just a list of pointers, pointing at different interrupts, at different positions. Next, we have what we call PDA. That's the BIOS data area. When the BIOS is started, it checks the devices, it checks the computer, and it allocates that to the next 256 bytes. Here we have information that we will see in detail in a minute. Then we have free RAM. This is a special sort of RAM memory. This is 7C00. This is where the BIOS will be reading the startup device for sector 0, mapping it into that address, 7C00. That's why it's such an important address. OVMR and VBR are mapped into that address. Then there's more conventional memory, as you see next. And finally, this is the part of the memory we're interested in. This is where the virus will get in. We'll see the BDA in a second. Lots of calls will be made. Information from this chart is obsolete, by the way. Each BIOS vendor does whatever they like. There's no standards. There's only a small fraction of these things that is common. This is what we're interested in. Address 413 in hexadecimal. This is where BIOS stores the amount of RAM available, not the gigabytes we have. Here we will have 1 mega at most. With PC512 and others, that was 512 in hexadecimal. So there are parts of the memory that can be or not, depending on the memory, on how we use it. This could be there, this could not be there. So once we know what we're looking at, we can start our analysis. This is the initial code. What does the VBR do? We are on the code for the BootKit itself. The first thing it will do is to copy itself into another memory space. Before it does that, it will modify address 4013. It will tell it, my code occupies 3 Ks, go here, remove 3 pages of memory, and allocate that to me. So when a program tries to allocate memory to that space, it will have to move upwards. I've just made a reservation. I've just reserved memory. So once that memory has been reserved, it is copied to whatever it corresponds. Once that is copied, it reallocates the code and it jumps into the code. What you see here is just the SB. This will copy the original VBR. Brosnis has the VBR, which is going onto the MBR, but it's got the original with APAC. It's compressed. In the demo you see here, I've cleaned everything so that it looks more clear for simplicity. So it does the depack for that area and stores it in 7C00 again. The only thing left is to use a controller for interrupt 15. It installs a controller for interrupt 15. By doing this, it restores the system, the control over to the original system. The only thing is interrupt 15 that hasn't touched. After doing that, it will calculate. Give me a second. In everything we've seen so far, we've seen how the BootKit is stored in 9F00. It updates address 4013. It controls interrupt number 15, and then it uses that address 9AC0. This is just a driver. It will be injected into Windows. So why does it go to interrupt number 15 in the first place? Well, it is used because this is for the memory map. This is used for the memory map of the entire system. There are calls made to that address from boot manager 16. By using interrupt 15, two things are possible. Next time a call is made from boot manager 16, the bootkit will be able to control whatever comes from it. It returns the memory pages in the system. Now we're in the memory area. If no one tells the system that we are there, the next loads in the system can delete that memory. So by using interrupt 15, we're able to check whether information is being sent to that address space. If so, it is rectified so that enough space is allocated. So it is a persistent use of memory. That's the key, that's the point. Interrupt 15 allows for that. So it loads things in memory. In previous versions, they would use interrupt 13. The reason for that is that there's lots of people that have been investigating in Black Hat and others. The guys building this have investigated those investigations and improved on them. So they decided not to go for interrupt 13, which is more conspicuous. So they go into interrupt 15, they use it once, and that's it. So let's take a look at that interrupt 15. What happens inside? This is what is installed when interrupt 15 is invoked. The first thing it will do is to check whether there was a call from a certain memory area. If that is the case, it will execute the normal interrupt 15. It will alter the data when a call is made to that. LA20. This is what returns memory pages. If that happens, it redirects code underneath. On the other hand, the first time a call is made to interrupt 15, this function is invoked. This function is called finding bytes inside boot manager. This is what that function does. It will look inside boot manager for a sequence of bytes that will have the system in protected mode. If we take a look here, it will patch the area. It will include a hook for that instruction. You see that here. MOVCR0 ARX. It will go into protected mode. If we went into protected mode, if we allow the system to go into protected mode, we lose IBT. Therefore, Rodness can do nothing. It needs to persist. It needs to live inside the system. So in order to do that, it goes here into this mode, and when the system is about to go into protected mode, it will use its own code to do whatever it needs. That's the reason why it uses interrupt 15. So mystery resolved. In order to persist, it needs interrupt 15. But this is the ideal way for them. They kill two birds with the same stone. They know the memory available in the system, and they persist in the area they're interested in. So why does it patch boot manager? Well, if we went into real mode, we would lose the interrupt. If you're in real mode, you call interrupt 15. It's there interrupt 15. If you're in protected mode, it's a different interrupt. So here, before the processor takes the system into protected mode, it establishes its own IDT and will alter it, will amend it. In the instructions, we have the LGDT that loads the global descriptor table. I will not talk about that because it's quite a mess. And LIDT loads the interrupt description table. A value is assigned to IDT. When there is an interrupt in the protected mode, it goes to the log to see what is in that memory space, and it will go into whatever position it says, +0. Interrupt 2, position 8. So IDT, I can't remember whether it was 4 or 8. So it applies a patch here on CR0. Once that patch is applied, we'll see what it does. We keep tracing, we get to that part of the code. This is the code that was run when we were supposed to go into protected mode. Instead of doing that, it jumps into that address and establishes the hook, runs the hook. So when it returns the answer from that question, from that function, it will go back to the initial instruction, and then it restores the initial instruction. It restores the same instruction back to its original state. So it will be ZR0AX. On the other hand, there is a call here, and there's IDT passed into it. That call establishes a controller for interrupt 1. When there is interrupt 1 happening, and since the IDT was set up in the way they were interested, what Runnews does is alter again the IDT. If I go to IDT, if it's interrupt number 1, go to my code. Interrupt 15 finds a pattern, they establish where the information should be stored, and they get interrupt 1. So mystery number 2 resolved as well. But what does the handler do with interrupt 1? What happens here? Here things get a bit complicated. Bear in mind that we're in protected mode. We can be in 32 bytes or in 64-byte mode. This bootkit is compatible with both modes. So how does he find out what mode it is in? You can only do this by accessing the registry of the system, or by playing a trick. Let me show you. Take a look at this instruction. If the processor is in 32-bit mode, you will see that code. If it's in 64-bit mode, this will have a prefix, 48 in this case. In AX64, the prefix indicates that the elements we're about to alter are 64 bits. If this code is seen in 64 bits, that DEC-AX disappears and becomes part of the instruction at the bottom. RSP plus 1C. What happens there? That's 32 bits. AX is set to 0 somewhere. Yeah. Short AX, that's 0. So it now knows whether the system is running in 32 or 64-bit modes. If it's 64-bit, it is not interested, it doesn't do anything else. If it's in 32-bit mode, it knows that there is interrupt 1 occurring. Interrupt 1 is looking at what happened. Interrupt 1 has been placed. By creating a handler for interrupt 1, it will tell the processor, if someone tries to read the IDT, I want this to go off. So every time the processor tries to read the IDT for whatever purpose, there will be interrupt 1. The first time interrupt 1 goes off, it will try and find a pattern calling this function. If it doesn't find it, it will activate track flag. Track flag, it's an internal registry for the internal debugger for the system, so that from that moment onwards, any execution of any instruction activates interrupt 1. If it isn't, breakpoints are removed and I go into the other mode. From then on, every instruction executed will call interrupt 1. So it will look for the interesting part. If it finds it, okay, it will be completed. If not, it will keep looking. What is it looking for anyway? It's looking for... Where is it? It's looking for a certain call within a range. Once it finds that call EAX, this is what it's looking for. Once it finds that call, it patches it. And it adjusts the address so that when there is a call to that address, it goes into there. So what does the handler for interrupt 1 does? If the processor is in 64-bit mode, it leaves. If interrupt 1 was not produced by an LGDD instruction, It exits by activating trap flag. Activating trap flag ensures that every time an instruction is executed, there's an interrupt 1. When it finds the LDT instruction, it looks in the next bytes for call reg and it patches it. So they now have it now has been introduced into a different part of the system. But what is it patching? It is patching a function in Boot Manager 32. This is important. Arch x86 transferred to 64-bit application ASM. Beautiful name. We know that that transfers control to a 64-bit application. That's it. And since we have the information, we open it up. It looked for this instruction. When it found it, it put the processor in trap mode and started executing all the instructions, one after the other, until it found this one. So it said, okay, I've found this instruction. Now that I have it, I keep looking farther down, and once I get to the right place, I apply a patch. The core EAX is calling the entry point for WinLoad. That's loading Windows. WinLoad is in charge of loading Windows. So what does the patch do here? It restores the original call. It adjusts the input, and it will look for two functions within WinLoad. The first one, OSL Arch Transfer to Kernel, and OSL P Load All Modules. Once it finds the functions, it applies one patch to each one, returning control to the original call reg that will call the entry point for WinLoad. Mystery 3 result. It was looking for a sequence in order to apply the patch. So everything we've seen so far, the main purpose is to survive to different changes in the processor and patch WinLoad.exit. So far, it's patched everything, and it's persisted in memory. We have a driver somewhere in the memory. So we'll take a look at the process. That's been a lot of details, I know. So let me show you graphically. System starts with the BIOS, it goes onto the MBR, goes into the BBR with the BootKit. The BootKit has a payload with modification of IVT, memory code VBR, original VBR, boot manager 16, changing to protected mode, then into payload, handler of interrupt 1, boot manager 32, getting in, that calls interrupt 1, interrupt 1 changes all the code here, it runs the original code, but now we have a patch in WinLoad. This is what happened so far. It's easier to see this this way, rather than giving you a full description of all the details. But why is it so interested in WinLoad? Well, because this is the part of the system that loads the kernel of the operating system, the kernel of Windows.
Lo hace para obtener una función de ahí que aloja memoria, ¿vale? Y el hook que establece en transfer, en OSL reals to transfer to kernel, ¿vale? Lo usa para ejecutarse él antes que el kernel. Él quiere hacer una cosita antes que el kernel, que ahora la veremos, ¿vale? Una vez ejecutado cada hook, restaura el código original. Ojo, hasta este momento el sistema ha confiado completamente en lo que había en él, ¿vale? Aquí no hay ningún mecanismo de defensa hasta ahora. Los mecanismos de defensa los va a activar WinLoad, ¿vale? WinLoad, si intenta cargar un driver, va a buscar sus firmas. Si la firma no es correcta y sus certificados no son correctos, pues va a pegar un error y no va a dejar que ese driver se cargue. ¿Bien?
If the certifications are not correct, we'll hook leave it in overslop modes, only establishing a hook by establishing BLMD allocate manager buffer. It parties in order to call the hook code, which is going to decipher the driver on 9AC00, calling there uploads modules, and abruptly says, I have a driver back in the memory on BIOS, please decipher it, put it on the memory address. Menu takes and calls the BLME allocate manager buffer on real mode. On the place you can see call MPA in place for Windows to recognize this. In the kernels, Windows has by calling B element allocate manager buffer by uh, putting the pointer where the driver is not loading, it's moving memory from one place to the other. Only the place Windows knows how to read it, and it's under the protections under Windows. If it's using Windows functions, Windows defense is jump off. This is not certified, this is not guarantee at all. Something wrong will happen. But he will tell me, okay, Windows does not want to load it, I will load it myself. So I'm going to this memory space, I log it, I check the IP. This is a PA file. It resolves the imports, and this is it. SCP, it takes this one thing for the other and leaves it there. Here you can see the code. It restored the patch. Uh, it looks for a certain value and calls located a manager buffer. This is what's going on. This is the parameter um, indicating there is a resetting of memory in the kernel nucleus. There's the remaining hook established, which is going to take the control before Windows takes the control. Once this real jump is executed, we will have the kernel core being executed and initialized. Is lodged, and I want to load it. It has to be loaded in some place. So it's going to look for certain structures, the kernel base, and it looks for something called a loaded parameter. No information about this anywhere. I don't know what the Russians got from that. They were hidden about. I have to do so many things. I talked to a fellow member, a colleague who could access this information. I never knew back from him. Uh, Nothing about this. This is a list where we can see Windows is going to tell me, okay, the operating system needs a disk system accessing the keyboard, the video, drivers, certain basic drivers. Windows will load it on memory. Windows will generate the parameter blocks, and Windows kernels will be called. I have this on memory. I will initialize. I have this and this and so on and so on. It obtains this information, and after obtaining this information, I'm gonna get the entry point, and I will have this driver in memory. Where is the entry code on my driver at this point? So at this moment, I will execute my driver for the Windows entering. The driver is prepared internally for it to, on the switch case, if you have called me on this point of the operating system, you will resolve yourselves so that the kernel base is moving up. You can look for the imports to the IPS headings. It patches itself, it resolves itself, and when it's totally resolved and loaded onto memory, it creates a copy of what is on a larger parameter block, and it's altered by saying that this corresponds to what we had been mapping before. Nothing. He took and has mapped a driver onto the system. When Windows passes the control to an NET kernel, we'll be calling a function what driver load it, and this is legal, it's working, it's going super good. What Robnis got. Robnis got into the system and registered driver without certification. It has the control of the system. As you have seen, there is some difficulties about tracing this from initial point. Some you never know how this reached to that point. You can analyze, you can remove this infection. Why are you doing this? You need to know where the originally is after this analysis. There is an action. We can debug book manager 32. If you activate the debugger, the virus disappears. It doesn't work. Do you remember the interruption one? Virus needed interruption one to propagate into the system. Any de- debugger installs interruption one, which is used to debug. In such a way, we try to debug all of these with Windows tools, and we activate boot manager debugger. No interruption one will take place because Windows NG will interpret that everything is booted normally, no infection. I don't know if it's a defense technique or undesired effect, but it's some interesting thing. After conducting the analysis, it's important for us to know how we can remove this from the operating system. For us to eliminate a bootkit is extremely easy. You restore the MBR or the VBR, and this is removed. By detecting on the country on an infected system that you have affected failed MBR and VBR is complicated because these viruses use hiding techniques that use roughness. Roughness falsify petitions of the system. If you try to open a witness on the system, move this from this to sector 0, it's going to show you sector 0 and full of zeros. This is a file they have because it costs us nothing. On this side, we can detect it roughly easily because you can read information sent to 0. Oh, what on earth this is being launched if it's on 0? This is a failure from himself. There is a process filter, roughness taking system to control. So any processes in the system, they know they had been launched. A process is bootkit detectors ultra wide. Don't execute it. Otherwise, I will shut down. It can control data received by application. It can inject a TLA, whatever they want to. As I said before, this is the kit, and the Robney developers introduce and file what DLA has to be loaded, and this is a TX key. You inject it, and this the LR Robney injected. Period. Never happens. Never happens. It has a virtual file systems. It takes some sectors of the hard disks. It lodges on something similar to a FAT encrypted with R6. Everything is going to be put and fitting in there. You load it on the hard disk, and you have an uncipher file. They make sure that it never goes through the hard disk. On the virtual systems injected on an user line in your Explorer, on your data management program, and from then on, they can do whatever they like. These folks have stack TCP/IP functions at the kernel level, at the kernel Windows. They had put it inside the driver the whole protocol. I don't know how many people developing this virus. Oh my goodness, they had a tremendous job, but they did it for a lot of money. Like I said, they have done a good research job based upon the rootkit, something presented on Black Hat, using interruption 13, based upon papers from this guy. You can check them out. And other techniques regarding concealment had been taken from this book. In this book, they explain to us very clearly all the techniques we had commented about defending against detection. The part of injections on Windows 8, these functions seem to have been taken from Robney, author and creator. They investigate a lot about getting this infection. Now I'm going to show you um, demo of a real virus executing itself in per se. I'm not going to plug in the virtual machine. This system is infected with roughnecks. I'm gonna open up a WinHex. Let's check them. The, this sector we open up. We go to the primary partition window. This is the VMR. It's like a launch and booted system. Since they have applied some filters for it not to see it, they have a failure in their implementation, and I'm quit. Skip it. We can see what this person wants to hide from us with this kind of filter, and here we have what it should be there. When you study something, you know how to break it for good reasons or bad reasons. This is a real machine. Robnits are executing the LAs for the rep. This is my demo. Now, this is the modified Robnits I have been using for this presentation. We're gonna see Windows affected by a rootkit doing the very same thing as Robnit with some differences. They do the same thing as Robnits when doing the patches up to Windows. From then on, there's no similarities. Some routines that change Windows logos and so on. Sorry, this is not working. This is Windows 7 x32 infected by a Robnit's modified version. Let's open up the hard disk and we'll see that so this is not the only one. You can see on screen that we are under the influence of rootkit. The rootkit has changed the logos, the window logo type. This is the beginning, the initialization. 40 cats is occupied by this logo. I have only 5K size to do the whole stuff. Let's execute window LG. No mainline rootkit will show and teach these messages from kernel. I'm here. No, this is not realistic. We finished an Explorer and we have created the Explorer process. This is the whole system hacked from inception. Something that split our hairs. With a low functioning rootkit, we can sign everything. The very first thing we want is to access the disk with Next, as we did before, to check the sector 0. Sector 0 on the hard disk, which should be on the launch sector. Sector 0, invalid partition table. As program scheduled for demo, I created a function that can load any driver without signature. Now, this driver is loaded onto the system with no certification at all. I'm not working for Microsoft for this to be loaded. You have it loaded, and for you to notice that it's loaded, let's read sector 0. To avoid readings, I'm open up and shut down, and from then on, a filter will be established that will not allow us to read this sector. We got a failure. I won't show this sector, and the BootKits is telling me I'm the filter. Sector 0 is blocked. No readings. So far, so good. As commented before, but it's working on Windows 7, 32, 64, Windows 10, and so on. We are wrapping up our presentation. 2 more demos. And let's see how this can be booted and launched on any operating system. Windows 7 has the I changed logo type text, and in the other one I only changed the logo. This is created for the demo. You can see that the root is working. But rootkit, being really malign, will tell you I'm being booted here. This is a super secure and super cool version. This is a screen. I will open up the BootKit to check and prove that the system is compromised, capturing the kernel events, created process, destroyed process with home edition. This is 64 bits. Let's check the remaining one. This is an 8.1 version. The logo, we show that the system is infected. I didn't touch anything. I tried to do further up, but it's further down. It shows how the system is launched. We'll see a debug, and we'll see the book active. Windows 8.1, Windows this 0. I don't know if this version is old or new. I have this image installed. The root is active on Windows 8, 8.1.64 bits. And lastly, I don't know if it will be the very first one. It could be the very first BootKit for on Windows 10. This proof of concept I created with a server in the background to see how many things we can do with a BootKit under system. And once again, the wicked people use it to put viruses inside. I use these tools because for me there are tools to fight against this. I do a lot of malware analysis by using BootKits as this as such. They allow me to trace that the malware is executed, because being myself on a core and kernel nuclear, I can see the spams process. I can inject my process from one malware and I can control it and see the information they are sending. That's why BootKits and rootkits. I'm not saying this is a malign thing. It's depending on the usage of them by you. Of course, this demo was a malign usage of Windows 10 is now booted. Let's open the debugging. There are some messages. Windows 10 professionals, versions 64 bits. We activate the kernel capture. We're waiting for something to happen. We got here. They're telling me process have been created, and the system is totally compromised. We can destroy and knock down drivers and whatever we want to. And this is the length of my presentation. I want to show you the problems regarding debugging these issues, how you need to set up an environment, all the information required which is not available on the internet. The slides, I have so many slides I didn't show you, which explain the whole configuration, how to compile bots and so much what booted and rooted will publish in all this. This will be the guidelines for you to check it online with the rooted information. I want to see what this guy tested on in front of us. I have some time. I have some extra time. Okay, I will show you an extra slide and demo I was working on during the weekend. It was Raider Code 2. I'm gonna launch the demo. Box executors behind with the console addressed to the Raider 2. Raider 2 traces the system in the visual mode with all the functionalities for radar 2 on visual mode. I will tell you that is radar is still a working version. I corrected some mistakes this morning. There are still lacking some manual things regarding the type of bases. But as I'm typing, bits equals to 16 to take on the assembly. We can do a step in to move on to the functions. This is the bias. This is the tracing of the bias. We can insert pre-points as I'm doing now on screen. So far so good. This is a breakpoint, this direction. Show me this breakpoint. Executed. And behind a watch is being executed. The profiles I mentioned before. The boot will load. I will launch a normal Windows if everything works properly. This will be a step at a certain moment. When interruption executed, the one doing patches, I will show that the debugging is failing. But perhaps I'm gonna have a breakdown on stage in front of you. It stopped. So it's working. It's working properly, my demo. We'll stop him in this address. I will show the remaining thing for removing 64 and 32 bits. This is the limbo instruction. I will do a disassemble 3 functions from where I'm on now. This is the SOR IX. This was 32 code. Show me the code on 32 bits, please. ASN BITS equals to 32. Configure state variable AMS bits not found. Well written. My goodness. We do this. We have the IX, which mentioned before, the 64 bits code. How easy radar is doing and giving me to do these conveniences. Otherwise, you should have used so many other menus. When you are on 32 bit, we can see the code, the SOR RX, where SOR RX disappears, and 48 starts being part of the instruction, and the registers is going to have 64 bits format. When you do this, if it's a 32 code, you are doing a decrease and a detriment of the thing, so you can use it on the screen. I hope you didn't get exhausted and tired and bored. Thank you for your attendance and your attention.
¿Preguntas?
Please, questions? Please stand up in order to ask the questions. The question: what methods can you use to infect with rootkit? You mean methods with Windows? How rootkit can be infected in a normal machine? Here, that reach your machine, the only did that the user has to execute. You have to execute this file like caramel. It uses scale-out privileges on Windows. You get on the migration wafer. When you are migrating your profile, they put a DLL onto the MyWiv folder for the migration, and this is executed with privileges. This allows us to write directly on the hard disks. Infection is done through direct access onto the hard disks and writing on the sectors. It's not a very sophisticated technique. you got this, is what execute this elevated and uploaded privilege because you are normally asked, this is going to do bad things onto the system. Are you allowing them to do so? And period. But it didn't do anything special on Windows 8.1 and 10. They didn't infect because the escalation privilege is cut down on Windows. They don't allow us to write on the sectors, but I don't doubt they could make increases and improvements. These codes are available on the network. You can touch it, you can modify it. I do it myself for a demo, so the wiki guy can do it on its own. Very firstly, my congratulations for your wonderful presentation. You have a super cool technical level, my friend. Well, I can't spot you on stage. What strikes me and astonishes me is the stacked ITCP. I understand this is down for you to be debugging the traffic of RTC on Windows is down for this, for you not to see it. They are analyzing boards and patterns. To what extent is this implemented the layer of TCP and up to the TCP of the interwoven patterns? I didn't investigate it very much because I want I didn't it's not my topic. You can check the alter falsify code. I would say they used it to talk with the CNC so they implement ICP. It was very modified and it substituted many things. In the comments, another interesting thing. This is it's commented in Russian language, by the way. The Russians talk about this. These emulate a start ICP, ICP in Russian written. My goodness, these guys knew what they're talking about. I don't know it was the person tampering with this code because there was such a tremendous, brilliant technical level behind it with spectacular information you cannot really access on a regular basis in Microsoft. They have doing so much reversing in the background. Question, please. My congrats. Very interesting presentation. When you patch the IBT for interruption 1, you correct the UBT on real mode. On real mode, you patch 15 in protected mode, you move it onto 1 to mold the window. This interruption number 1 is on trap mode, following the instruction. When you have hooked the the load functions, so on, you don't really need for the interaction to continue. I forgot to tell you before, when the function searched by the pattern is found, is deactivated later on. The handling is readjusted and reinstalled after on originally. In fact, it's not. They deactivate the breakpoints. I modified and deactivated when it happens, but then it deactivates when the load is done. The DR6, which is the controls register, put it, and IT points at that. It's dirty place, but you can look for that on that area. I think when it was lag, and somebody put some dirty thing in between the rabbits because the technical quality you have commented on, or when the BR is falsified, and this is illogical in something that's at such tremendous level. The one who lacked the system forget about something which you consider not to be relevant.
One very quick question, Abel. Hardware chips for cryptography, shouldn't they include a functionality to validate the last valid VBR? Well, they're implementing this, and Box is based on that. The problem is that when you have an EFI BIOS, or EFI, you can create your own EFI module to do a function or whatever you want. But once you do that, what else is left? They were talking about this recently. Until vendors reach a standard for the industry to verify that a module is valid or legitimate, there's nothing else we can do. You can verify that the loader is genuine for Windows, but if you buy a laptop, try to install Linux. It will not allow you. Very well. Thank you very much, Abel.